The night sky could one day be filled with colossal, engineered worlds. This is the promise of megastructure engineering, a real field of theoretical science. We are going to explore 20 of the most staggering theoretical megastructures any civilization could ever build. By the end, you will understand the ultimate potential of intelligence in our universe. What does it take to turn a star into a power plant, or a planet into a computer? How could a society build a home that loops around its sun like a cosmic ring? I want you to think about the very nature of ambition. What does it mean for a species to truly grow up? The year was 1929, a full century before you and I are having this conversation. A scientist named John Desmond Bernal looked past the rockets and airplanes of his day and sketched out a vision of something profoundly different. He described a hollow sphere, a world built not from rock and soil, but from engineering and intent, designed to house a civilization in space. This was not yet a megastructure, but it was the seed. The idea lay dormant for decades, a curious footnote in the history of futurism, waiting for a mind that could give it real scientific weight. That mind belonged to Freeman Dyson. In 1960, the physicist published a paper that would change everything. He wasn't writing a blueprint for construction. He was solving a detective's puzzle. How would we find another advanced civilization, he asked, if it existed? His answer was breathtakingly logical. Any species that keeps growing will eventually need all the energy its home star produces. So, look for stars that behave strangely. Look for a sun whose visible light is dimmed, but whose infrared heat signature glows brightly, because something is capturing that starlight and re-radiating the waste heat. He envisioned a vast, loose swarm of energy collectors, a cloud of satellites encircling the star. The media and science fiction latched onto this, calling it a Dyson sphere, often picturing a solid, impossible shell. But the core idea was far more powerful. It was a signature, a civilization's footprint on a galactic scale. This single thought experiment broke a psychological barrier. It moved the goalposts of ambition from the surface of a planet to the volume of a solar system. Suddenly, the conversation was no longer about better rockets or bigger space stations. It was about stellar engineering. What followed was an explosion of theoretical design, each concept more staggering than the last, each one asking a deeper question. These are not just exercises in cosmic architecture. They sit at a rare crossroads where hard physics meets profound philosophy. They force us to ask what a truly mature civilization looks like. Is its defining trait the need for unimaginable amounts of energy, or is it the drive to create a permanent, stable home? Could it be the desire to compute the universe's deepest secrets, or perhaps to leave a monument that outlasts the stars themselves? Every megastructure we will explore is an answer to one of these existential questions. They represent projects that would span not years, but thousands of years, demanding a level of societal patience and unified purpose we have never known. So as we journey through these 20 concepts, remember this shift in perspective. We are no longer thinking like inhabitants of a world. We are beginning to think like shapers of a solar system. So the difference is one of category, not just degree. A skyscraper is a building, a city is a collection of buildings, but a megastructure is something else entirely. It is a single engineered object with a scale and a purpose that redefines what a civilization is capable of. Think of it this way: we build houses to live in. We build power plants to energize our cities. A megastructure often merges these ideas into one colossal entity, but at a level so vast it becomes a new feature of the solar system itself. There are three lenses through which we can understand this. First, scale. We are not talking about something a few miles wide. We are talking about structures whose smallest meaningful measurement is the distance between planets. If you were to walk the circumference of one, the journey would take lifetimes. Second, purpose. This is not a bigger apartment complex. A megastructure addresses a foundational need for an entire species. It might aim to capture every single photon of light from a star, to provide living space for trillions of beings, or to create a bridge between suns. Its function is existential. And third, transformative impact. A successful megastructure does not just add to a civilization, it changes the civilization's very relationship with reality. It solves a problem so completely that the species evolves into something new on the other side of its construction. With that framework, we can start to group these cosmic ambitions. Some are engines designed to harness energy, others are arcs designed for permanent habitation, a few are gateways for travel or communication across the void. And some are minds built to perform calculations or observations beyond any biological brain. Each one we will explore represents a different answer to the ultimate question of growth. What does a society do when it has outgrown its cradle? The answer begins with our first concept, a structure so iconic it has shaped our dreams of the future for generations. It is the ultimate habitat, a ribbon of world looping around a star. That ultimate habitat is known as a Ringworld, a concept we will return to. But before you can build a home of that scale, you need the power to run it. This brings us to the foundational megastructure, the one that started it all. The Dyson sphere is not a solid shell. That popular image is a beautiful but impossible idea. A rigid sphere around a star would be torn apart by gravity, crashing into the sun it was meant to harness. The real concept, as Freeman Dyson envisioned it, is far more dynamic and achievable. Think of it as the ultimate power grid for a solar system. A civilization reaching this level would find that the combined energy of all its planets is just a drop in the bucket. Its growing needs, from computation to industry to sheer living space, would demand something more. The solution is to go straight to the source. Imagine a vast, coordinated cloud of millions, even billions, of individual satellites. Each one is a solar collector, a mirror, or even a habitat with its own power array. They do not form a solid wall, but a dense, intelligent swarm in orbit around their star, capturing nearly every single photon of light it produces. This is a Dyson swarm. Each unit in this celestial fleet could have a specialized purpose. Some might be pure energy harvesters, absorbing sunlight and converting it into a form of power that can be transmitted. They might beam this energy via focused lasers or microwaves to distant colonies, construction sites, or other megastructures hungry for power. Other units in the swarm could be factories, building more of themselves in an exponential wave of growth. Some might even be habitats, cities floating in the eternal daylight of their engineered sun. The scale of material required for such a project is almost beyond comprehension. It would not come from asteroid mining alone. The most likely source would be the systematic disassembly of an entire planet, perhaps a gas giant like Jupiter or a rocky world that is no longer needed. This process, known as planetary mining or astroengineering, would provide the raw elements to manufacture the swarm's components on an industrial scale that makes all of human history look like a single workshop. Completing a Dyson swarm represents a fundamental milestone. It marks a civilization's graduation to what we call a Type 2 on the Kardashev scale. This is a theoretical framework that measures a civilization's advancement by its energy use. A Type 2 civilization does not just use the energy that falls on its planet, it captures the total output of its star. This is the first, essential step into a true era of cosmic engineering. It is also a cosmic signature. From a distance, such a star would look strange to our telescopes. Its visible light would be dimmed, blocked by the swarm, but it would glow fiercely in the infrared spectrum from all the waste heat the collectors radiate. To a distant observer, it would be a beacon screaming that something intelligent has taken charge of an entire solar system. It is the ultimate declaration that a species has outgrown its cradle and is now building its own future, photon by captured photon. But a Dyson swarm is just the beginning, the power source for ambitions far grander than simple energy collection. With that unimaginable energy budget, what do you build? If the ultimate goal is to provide a permanent, stable home for a civilization that may number in the trillions, you need more than a cloud of satellites. You need a world, not a planet, but something engineered from the ground up, or rather, from the stellar forge outward. This brings us to the second megastructure, a concept that stretches the idea of a habitable surface to its absolute, breathtaking limit. It is called the Alderson Disc. Picture a structure so vast it defies every instinct we have about where life can exist. Think of a cosmic compact disk, a solid, flat plane of engineered material with a hole cut perfectly in its center. Through that hole at the exact middle sits the system's star. This is not a ring. It is a full disk, a single, continuous surface that stretches from a point perhaps as close as Mercury's orbit all the way out to the distance of Mars or even Jupiter. The scale is incomprehensible. The disk would be thousands of miles thick to provide both structural integrity and the mass needed to generate its own surface gravity. You would not live on the top or the bottom. You would live on either of the two inner faces, the vast planes that face the central sun. Gravity would pull you toward the surface of the disk, meaning the sun is always fixed at high noon in your sky, a perpetual, unmoving beacon. The environment on this superworld would be defined by one thing: distance from the center. The inner rim, skirting close to the star, would be a scorching, molten hellscape. The outer rim, far out in the darkness, would be a frozen, airless plain. But between these two extremes lies a band, a habitable zone millions of miles in width, where the light from the central sun provides just the right amount of warmth. This is the true territory of the Alderson Disc. Within this golden band, an advanced civilization could sculpt continents, oceans, and atmospheres. They could create climates of endless variety, from eternal tropical coasts to vast, temperate forests, all on a single, unbroken plane. The living area here is not just double that of Earth, it is millions of times greater. Every human who has ever lived could have their own continent, with space left over for endless wilderness. The engineering challenges, of course, are beyond staggering. They border on magic with our current understanding. First, you need a material with impossible strength. No known substance could withstand the titanic gravitational, centrifugal, and thermal stresses without shattering like glass. Some theorists suggest a foundation of active support, using unimaginably powerful magnetic or gravitational fields to hold the disk together, a technology we can scarcely dream of. Second, you must manage the star itself. Solar flares and coronal mass ejections would lash the inner regions, requiring planetary-scale magnetic shields. The disk's own gravity would also constantly tug on the star, potentially pulling it out of the perfect center, requiring constant, precise adjustments to maintain stability. Yet the philosophical payoff is profound. An Alderson Disc represents the ultimate act of terraforming. It is not about adapting to a world you find, but building the exact world you need from raw matter and will. It answers the question of living space with a definitive, almost overwhelming solution. It creates a stage so vast that the entire history of a species could play out across its surface without ever repeating the same scene. It turns a solar system from a collection of disparate orbs into a single, engineered habitat, a sun-belt superworld where the day never ends and the horizons are literally endless. This idea of a continuous, engineered surface pushes our thinking to the brink, forcing us to ask what comes next when even a disk the size of a solar system is not enough. The Alderson Disc offers a plane of endless horizons, but it demands we invent physics to hold it together. There is another vision, equally grand but built upon a principle we already understand, a ribbon of world that turns a star into the centerpiece of a cosmic carousel. This is the Ringworld, an idea that leapt from the pages of Larry Niven's science fiction and into the serious conversations of physicists. Its elegance is in its simplicity. Picture a band, a flat, million-mile-wide ribbon, bent into a perfect circle with our Sun at its center. It orbits at the same distance Earth does, but this is not a planet. It is a single, continuous strip of engineered land, its inner surface forever turned toward the light. On this inner surface, an advanced civilization could paint a landscape of staggering diversity. They could sculpt continents larger than Asia, carve seas deeper than the Marianas Trench, and raise mountain ranges that vanish into a permanent, sunlit sky. The ring spins not to orbit the star, but to create gravity. Centrifugal force pins everything to that inner landscape, just as a spinning amusement park ride pins you to the wall. To hold in a breathable atmosphere, the engineers would need walls. Not simple fences, but towering cliffs 1,000 miles high running along each edge of the ribbon, containing an ocean of air. And to create the rhythm of day and night, a secondary ring of enormous orbiting panels called shadow squares would drift closer to the star, casting moving shadows across the land in a carefully choreographed celestial dance. The numbers alone are a form of poetry. The surface area of a single ring world equals that of several million Earths. Every human story that has ever been told could be given its own unique valley, its own river system, its own ecosystem, with endless room still left for unexplored wilderness. It represents a solution to expansion that feels almost luxurious in its generosity. Yet, for all its apparent stability, the ring world hides a fatal flaw. It is an unstable configuration. In a simple two-body system, a planet orbits a star because it is a small object moving around a massive one, but a ring world is a balanced, symmetrical structure. Any slight perturbation, any tiny shift would cause it to drift off-center. Without constant, precise correction, the entire ring would slowly, inevitably, slide toward its sun, a catastrophe of literally world-ending proportions. The builders would need what Niven called attitude jets, enormous thrusters built into the structure's frame, firing continuously to maintain perfect balance. This introduces a theme we will see again and again in megastructure engineering: the hidden cost of cosmic scale stability. Nothing this large is ever truly set and forgotten. It requires eternal vigilance, an unending application of power and intelligence to defy the subtle nudges of gravity. This relentless need for control leads us to a structure that does not fight orbital mechanics, but fully embraces them, turning the very instability of the ring world into its foundational principle. The ring world's need for constant, active correction reveals a deeper truth about cosmic engineering. Sometimes the most powerful structures are not those that dominate a star, but those that master the space just above a world. This brings us to a concept that feels almost within reach: a megastructure that could be the first true bridge between a planetary species and a spacefaring one. It is called the Orbital Ring, scaled down from the stellar ambitions of a Dyson swarm. Forget, for a moment, the epic planes of an Alderson Disc. Focus instead on the blue-green curve of a single planet like Earth. The fundamental bottleneck for any civilization on the verge of expansion is the gravity well. Launching anything from the surface is incredibly expensive, requiring massive amounts of fuel to achieve escape velocity. It is like trying to build a city by hauling every brick up a sheer cliff by hand. The orbital ring offers a permanent staircase. Imagine a slender, rigid hoop encircling the entire planet, not in traditional orbit, but held perfectly fixed in the sky. It is a geostationary ring forever positioned above a specific point on the equator, perhaps 22,000 miles above the surface. How does it stay up? It does not rely on fragile materials or impossible strengths. Instead, it uses a principle of momentum. Inside the ring is a vacuum tube, and racing through that tube at blistering speeds is a stream of particles or a loop of super-strong cable. This stream moves at orbital velocity, meaning its natural tendency is to fly off into space. The rigid outer ring holds it in, while the stream's momentum, in turn, holds the entire rigid ring aloft. It is a dynamic, active structure, a continuous flow of energy that creates a stable platform in the sky. From this impossibly high balcony, you can simply drop a cable. Not one space elevator, but dozens. These tethers descend all the way to the planet's surface, creating permanent, high-capacity routes to orbit. Moving up and down these cables could be as routine and energy efficient as taking a cross-continental train. The cost of reaching space would plummet to a fraction of what it is today. The ring itself becomes prime real estate. It is a continuous, zero-gravity strip wrapping the world. Here you could build vast solar power stations, capturing unfiltered sunlight 24 hours a day and beaming the energy down. You could place factories that manufacture products in perfect vacuum and microgravity, products impossible to make on Earth. You could even construct entire cities that circle the globe every few hours, offering a view that redefines the word window. The orbital ring is not about creating new living space, but about enabling everything that comes after it. It is an infrastructure megastructure. It solves the single biggest practical problem of becoming an interplanetary species. By making the movement of people and material into space cheap and routine, it unlocks the solar system. This idea shifts our perspective. A megastructure does not have to be a final, glorious home. It can be the ultimate tool, the key that opens the door to everything else. And if a ring around one planet is a key, then a ring connecting 2 points across the void is something far more profound, a bridge between worlds. While the orbital ring builds a permanent highway in the sky, another structure embraces motion itself, a spinning line that could turn the journey to orbit into a graceful, energy-efficient swing. This is the Skyhook, often called a momentum exchange tether. Picture a cosmic fishing line, hundreds or thousands of miles long, with its center of mass anchored in a stable orbit around a planet. The entire cable rotates end over end, like a slow-motion propeller blade sweeping through space. Here is the elegant trick. The tip of this rotating cable, at its lowest point, dips down into the very fringes of the atmosphere. Crucially, because it is rotating, not orbiting, this tip is moving much slower than orbital velocity. A spacecraft launching from the planet below would not need to fight its way all the way to orbit. It would only need to climb high enough to rendezvous with this slow-moving tip. It latches on like a trolley car grabbing an overhead cable. Then, the rotation of the Skyhook takes over. As the cable sweeps upward, it transfers its momentum to the spacecraft, gently but powerfully whipping it up to full orbital speed. The process works in reverse for landing, using the cable's motion to slow a vehicle down for a gentle atmospheric entry. The fuel savings are monumental, turning a launch from a violent, explosive struggle into something closer to catching a moving train. Now, imagine a network of these dynamic tethers. One Skyhook stationed in low Earth orbit could hand off payloads to a second, faster rotating Skyhook in a higher orbit, which could then fling them toward the Moon or to interplanetary transfer points. Around a world like Mars with its thin atmosphere, a Skyhook could be the primary port, effortlessly lifting and landing vehicles without the need for powerful rockets. This transforms a single planet's gravity well from a prison wall into a series of manageable steps. The Skyhook represents a different philosophy of megastructure engineering. It is not about creating permanent living space or capturing a star's energy. It is pure infrastructure, a tool for movement. It focuses on the problem of connection, making the vast distances within a solar system feel smaller and more navigable. It suggests that an advanced civilization's mastery might be seen not just in its grand monuments, but in the elegance of its transit systems, in the graceful arcs its vehicles trace between worlds. This focus on bridging gaps logically turns our gaze outward, past the familiar planets, to the unimaginable distances between the stars themselves. To cross that void, you would need more than a spinning cable. You would need a runway that stretches for light years. The Skyhook's elegant motion suggests a profound principle, that stability can be an active process, not a static state. This principle finds its ultimate expression in a structure that seems to laugh in the face of gravity itself. It is called the Space Fountain, and it is a tower that stands not on a foundation of rock, but on a river of speed. Forget everything you know about architecture. A traditional skyscraper is a careful stack of materials, each floor compressing the one below it, until the weight at the base becomes immense. There is a limit to how high you can build before the bottom crumbles. The Space Fountain rejects this entire idea. Instead of fighting compression, it avoids it entirely. Imagine a slender needle rising from the Earth's surface, piercing the atmosphere, reaching hundreds of miles into the blackness of space. Inside its core is not an elevator shaft, but a high-speed highway. A continuous stream of dense projectiles, perhaps small pellets of tungsten, is magnetically accelerated upward through a central tube at velocities of several kilometers per second. This is not a gentle flow, it is a torrent, a kinetic river. At the very peak of the tower, these projectiles encounter a powerful magnetic deflector. It does not stop them. Instead, it curves their path, sending them hurtling back down through a second, surrounding tube that encircles the upward stream. They complete the loop, returning to the base to be accelerated once more. This is the magic. The constant upward rush of mass possesses tremendous momentum. Physically, this momentum exerts an upward push against the magnetic deflector plate at the top. That plate is connected to the entire structure. So, the entire tower is literally being held up, kept from collapsing under Earth's gravity, by the sheer force of this internal, recirculating torrent. It is like balancing a pencil on the palm of your hand by constantly firing tiny bullets upward to hit its eraser. The tower is not standing, it is being actively supported every single microsecond. The engineering is, of course, phenomenally complex. It requires flawless magnetic levitation to prevent the projectiles from ever touching the tube walls, and an immense, constant power supply to maintain the stream against inevitable energy losses. But the payoff redefines possibility. A fully realized space fountain could reach past the atmosphere, its peak touching the realm of geostationary orbit. It would be the ultimate launch tower. Spacecraft could be assembled at the top, already in the vacuum of space, and simply released, needing only a small push to begin their journeys. The fountain itself could serve as a structural spine, a backbone upon which vast orbital platforms, research facilities, or even the beginnings of an orbital ring could be constructed. This is not a habitat, it is a tool of breathtaking ambition. The space fountain represents a fundamental shift in engineering philosophy, from passive mass to active momentum. It shows that for a civilization with enough energy and control, the very rules of construction can be rewritten. Gravity becomes not an absolute master, but a force to be dynamically negotiated. This mastery over foundational forces sets the stage for projects that move beyond mere infrastructure, toward structures whose purpose is to channel power on a scale that bends the fabric of space itself. The space fountain stands as a defiant column of motion, a kinetic defiance of gravity's quiet pull. Yet for all its towering ambition, it is ultimately a bridge, a means to an end. The true end for any civilization is a home, not a launch pad or a power grid, but a place where life can flourish under an open sky. This brings us to a vision that scales down the epic to the human, a structure that is not a continent in space but an island. It is the Bernal Sphere, the fundamental unit of life in the void. Proposed by John Desmond Bernal almost a century ago, this concept is beautifully simple in its geometry. Imagine a sphere perhaps 10 or 20 miles across, floating in the deep black. It rotates slowly, and on its inner equator, that spin creates a gentle, familiar pull artificial gravity. Here, along this vast, curving valley, an entire world is engineered. You would not stand on the outside of the sphere looking out at the stars. You would live on the inside, looking up at a complete, encapsulated landscape that arches over you. Towns would nestle into hillsides, forests would climb the gentle slopes, and lakes would gather in the lowlands, their water held in place by the same spin that holds you down. Overhead, a long, cylindrical mirror outside the sphere would track the sun, reflecting its light through great windows to create a perfect, controlled day and night cycle. The sky is not open space, but the opposite, distant wall of your world, painted with clouds and lit by a captured sunbeam. This is not a megastructure of staggering, impersonal scale. It is a habitat, a biosphere sealed against the absolute cold. Alongside designs like the Stanford Torus, a rotating wheel-shaped colony, the Bernal Sphere forms the foundational idea of the space colony. It answers the question of off-world living, not with infinite planes, but with a finite, perfect balance. Every element is curated, every nutrient cycle closed, every watt of energy accounted for. It is a terrarium for a civilization, a self-sustaining ark. The profound implication lies in replication. A mature species might not build one Bernal Sphere. It might construct millions of them, a glittering archipelago of artificial worlds scattered across the solar system. Each one could house a unique culture, a distinct ecosystem, a different chapter in the story of its people. In this vision, these spheres become the living cells of a Dyson swarm, the modular, biological component of a stellar engine. They are where the captured sunlight is ultimately spent on life itself. The Bernal Sphere reminds us that the ultimate goal of cosmic engineering is not just power or dominion, but the preservation and propagation of the fragile flame of biology. It shifts the narrative from conquering space to carefully curating pockets of home within it. This modular approach, building life-sustaining volumes one at a time, suggests a different path to the stars, one of patience, repetition, and profound care for the closed systems that keep us alive. And if we can create a stable world from nothing but metal and will, what stops us from creating a machine of similar scale, built for a purpose far beyond mere habitation? What happens when the megastructure is not a home but a mind? The Bernal Sphere is a home for biology, a sanctuary of soil and air. But what if the ultimate destiny of a civilization is not to build more homes, but to build a greater mind? This leads us to the eighth megastructure, a concept that redefines the purpose of a star. It is called the Matrioshka Brain, a star-sized computer. The name comes from the Russian nesting dolls, one fitting perfectly inside the next. That is the core of its design. We already have the foundation, a Dyson swarm harvesting a star's total energy output. But a simple swarm uses that energy for power, for light, for industry. The Matrioshka Brain asks a more profound question. What is the highest possible use of that energy? Its answer is information processing. Imagine taking that swarm and refining it into a precise, layered machine. The innermost layer is a dense sphere of computing elements orbiting extremely close to the star. These processors would be built to withstand blistering heat, using the star's most intense radiation as their power source. But no machine is perfectly efficient. They produce waste heat. In a normal system, that heat would just radiate away into space. Lost here, it becomes fuel. That waste heat warms a second, larger sphere of processors built just a little farther out. These units operate at a lower, optimal temperature, using the first layer's exhaust as their primary energy source. Their waste heat, in turn, warms a third layer, and so on, like a cosmic engine of nested thoughts, each shell running on the spent warmth of the one before it. The structure could have dozens of layers, each colder than the last, until the final, outermost layer radiates the last whispers of heat into the frigid void of interstellar space. In this vision, every single joule of energy from the star is put to work not for physical labor, but for computation. The entire construct becomes a single, integrated thinking engine on a scale that dwarfs all the computers humanity has ever built combined by a factor of trillions upon trillions. What could you possibly do with such a mind? The applications are as staggering as the machine itself. It could run simulations of entire universes, testing the laws of physics under every conceivable condition to uncover their deepest secrets. It could model the precise evolution of galaxies from the first second after the Big Bang to their distant cold end. It could solve problems in mathematics and engineering so complex they are literally unthinkable to a biological brain. Perhaps most intriguingly, it could become a substrate for consciousness itself. A civilization that has mastered its biology might choose to transcend its physical form, uploading the patterns of its minds into this vast, secure, eternal digital realm. The star computer would become their new universe, a reality of pure thought and experience, limited only by the laws of physics and the brilliance of their own code. The Matrioshka Brain represents a fundamental pivot in the story of a civilization. It is not about outward expansion, but inward depth. It shifts the narrative from conquering space to comprehending it, from building structures to building thoughts. It suggests that the final monument of a truly advanced species might be invisible, a silent, cool sphere of pure intellect orbiting a star, thinking thoughts as vast as the cosmos that birthed it. This pursuit of ultimate knowledge, however, demands more than just a powerful computer. It requires a perfect, stable vantage point, a platform for observation so grand it makes every telescope we have ever built look like a child's toy. A star is a fixed point in the sky, the anchor of a solar system. But what if a civilization needed to pull up that anchor and sail? The ninth megastructure answers this with staggering ambition. It is the stellar engine, a device built not to harness a star but to move it. The most famous design is known as the Shellworld thruster, a concept of beautiful, patient simplicity. Picture a colossal parabolic mirror, half of a Dyson sphere, positioned just outside a star's gravitational grip. It does not orbit. Instead, it floats in a delicate balance, held in place by the very force it uses for propulsion, the gentle but relentless pressure of starlight. Photons streaming from the star strike the mirror's vast, curved surface and bounce back. Each tiny photon carries momentum, and as it reflects, it gives a minuscule push. Across the entire mirror, trillions upon trillions of these reflections add up to a whisper of thrust, pushing the mirror away from the star. Because the mirror is held in place, that thrust is transferred to the star itself, nudging it slowly, imperceptibly, in the opposite direction. It is a cosmic sailboat, using light as its wind, with the star as both engine and cargo. The acceleration is glacial. A Shellworld thruster might move a star at only a few meters per second over a century. But time is the one resource a truly advanced civilization has in abundance. Over millions of years, this gentle pressure can add up to a significant change in velocity, enough to steer an entire solar system on a new course through the galaxy. Why would anyone undertake such a project? The reasons are as vast as the journey itself. Perhaps a neighboring star is destined to go supernova, a cosmic catastrophe that would sterilize every world for light years. A stellar engine offers an escape, a way to gently nudge your home out of the path of destruction. Or maybe a civilization looks toward the galactic core, a region dense with stars and resources, and decides to make the long pilgrimage inward. Conversely, it might seek the quieter, safer suburbs on the galaxy's outer rim. The star becomes a generational ship on the grandest possible scale, carrying its retinue of planets, habitats, and megastructures along with it. This transforms our understanding of a home. It is no longer a fortunate accident of location, a planet that happened to be in the right place. It becomes a chosen destination, a product of navigation spanning eons. The stellar engine represents the ultimate mastery of environment, treating the galaxy not as a fixed map, but as an ocean to be sailed. It shifts a civilization from being inhabitants of a solar system to being pilots of one. This idea of directed, purposeful motion on an astronomical scale inevitably leads to a question of destination. If you can steer your star, where would you go? The answer might not be a place of safety, but a place of profound connection, a meeting point for minds across the void. A star is a steady, predictable furnace, but a civilization seeking ultimate power might look to a far more extreme and efficient engine. This brings us to the 10th concept, a structure that treats the most destructive objects in the universe as industrial tools. It is the black hole farm. For a truly advanced species, black holes are not merely cosmic monsters to be avoided. They are potential power plants, gravitational anchors, and even waste disposals, all wrapped into one. The idea begins with the quest for efficiency. Even a Dyson sphere around a star is wasteful by the standards of pure physics. Nuclear fusion in a star converts only about 0.7% of its mass into energy. A matter-antimatter reactor would be 100% efficient, but is fantastically difficult to fuel. A black hole, however, offers a middle path of staggering potential. By feeding matter into a carefully managed black hole, up to 40% of that mass could be converted into usable energy through processes like the Penrose effect, where the intense rotational energy of the black hole itself is tapped. This is over 50 times more efficient than our Sun. The farm would need a reliable source of black holes. One method would be to capture small, primordial black holes, hypothetical remnants from the universe's first moments, drifting through interstellar space. Another, more proactive approach would be to create them artificially, perhaps by focusing unimaginable amounts of energy into a single point. These would be small black holes, perhaps no larger than a mountain but containing the mass of a planet. Each one would be housed in a secure containment facility, a complex of magnetic and gravitational fields to hold it in place. Matter, like hydrogen scooped from the interstellar medium, would be carefully fed into the black hole's accretion disk. As the material spirals inward, friction would heat it to billions of degrees, emitting torrents of X-rays and gamma rays that could be captured and converted into power. The smaller the black hole, the hotter it radiates, making it a more intense, if more volatile, energy source. But a farm implies multiple uses. The immense gravity of a small black hole could serve as a perfect anchor for other megastructures, providing a stable focal point in space. It could also be the ultimate waste disposal system, a cosmic incinerator where any material is reduced to its fundamental particles and energy. The most speculative concept, however, is the black hole bomb. In this theoretical construct, mirrors would be placed around a rotating black hole to trap radiation within its ergosphere, the region just outside the event horizon. Each time the radiation reflects, it steals a tiny amount of the black hole's rotational energy, amplifying itself in a runaway feedback loop. The result is a controllable, catastrophic energy release that could be harvested or, if mismanaged, could destroy the entire facility. This idea ventures to the very edge of known physics, where our equations begin to fray. Yet, it illustrates a profound shift in thinking. It suggests that the ultimate monuments of intelligence may not be beautiful habitats or powerful computers, but functional, industrial complexes that harness the raw, violent machinery of spacetime itself. It is the universe's most dangerous fire put to work. Harnessing a black hole's fury is the pinnacle of power generation, but it is a stationary, inward-focused ambition. To become a true galactic civilization, you must solve the problem of motion across the void. Rockets, with their need to carry their own reaction mass, are hopelessly inadequate for journeys spanning light years. The fuel required becomes the cargo, a self-defeating cycle of exponential growth. The 11th megastructure offers an elegant escape from this tyranny. It is the Interstellar Laser Highway, and it reimagines the very concept of a journey. Instead of packing your engine on board, you leave it at home. The core idea is a network of unimaginably powerful, precisely focused laser arrays constructed in orbit around a star. These are not simple beams of light. They are the product of a Dyson swarm's entire energy output, concentrated and collimated into a single, coherent push. A spacecraft destined for another star would not have a rocket engine. It would carry only a payload and a vast, gossamer-thin sail, perhaps miles across but thinner than a sheet of paper. This light sail is the only moving part. As it unfurls, it positions itself in the path of the waiting laser. When the beam engages, something magical happens. Photons, though massless, carry momentum. Trillions upon trillions of them striking the reflective sail impart a gentle, continuous, and unrelenting pressure. There is no explosion, no violent ignition. The spacecraft simply begins to move, accelerating with a smooth, silent force that builds over days or weeks. Because the power source is fixed and external, the spacecraft can reach velocities that are a significant fraction of the speed of light without ever carrying a drop of fuel. It is a cosmic slingshot where the sling is a star and the stone is an entire mission. But acceleration is only half the problem. How do you stop? The most ambitious vision of the laser highway involves a reciprocal system. The destination star system, perhaps settled by an earlier, slower voyage, would have constructed its own laser array. As the incoming craft approaches, the destination lasers fire not to push it away, but to act as a brake, catching the sail with a counterbeam of light to slow it down for a gentle arrival. This transforms the highway from a one-way launch system into a true two-way thoroughfare. The megastructure here is not the fragile sailcraft, but the permanent, monumental infrastructure left behind. The colossal laser stations, their Dyson swarm power grids, and the precise targeting systems that must hold a beam steady across light years of space. It represents a civilization thinking in terms of permanent routes, not solitary expeditions. It builds a bridge between suns, a path that can be used again and again by generation after generation of travelers. This changes interstellar expansion from a series of desperate, isolated leaps into a process of deliberate, systematic connection. It is the necessary infrastructure for a culture that thinks of the galaxy not as a collection of isolated islands, but as a single, vast neighborhood waiting to be linked by roads of light. The light of a laser highway connects stars, but the journey itself is only a prelude to arrival. You still need a place to live. For a civilization committed to life among the stars, the ideal home may not be a sphere or a disk, but something simpler and more efficient. This is the Alderson Cylinder, often called an O'Neill cylinder, and it is the workhorse habitat of a spacefaring age. Picture a colossal can, 20 miles across and 100 miles long, floating in the void. It rotates slowly, and on its vast inner curve, centrifugal force creates a gentle, familiar pull. This is where life takes root, not on the outside, but on the inside of the drum. You would stand on this curving landscape, with the ground arching up on either side until it met overhead, a complete world contained within a tube of metal and glass. The scale is both intimate and immense. Rivers could flow from one end cap to the other. Forests could climb the rising hills, and towns could dot a valley that stretches farther than the eye can see. Overhead, 3 longitudinal windows run the length of the cylinder, and outside, massive mirrors track the sun, reflecting its light inward to create a perfect artificial day. The blue strip of sky is not an atmosphere reaching to infinity, but the opposite wall of your world, 20 miles away, lit by captured sunshine. Compared to a Bernal Sphere, the cylinder is a design of elegant practicality. It offers far more usable living area per unit of material, a crucial consideration when you plan to build not one, but thousands. They would likely be constructed in pairs, spinning in opposite directions to cancel out gyroscopic effects and maintain a stable orientation. These twin worlds could be linked by a central hub, a zero-gravity docking port where shuttles arrive and depart. Imagine clusters of these cylinders, not just pairs, but dozens or hundreds, gathered at the stable Lagrange points of a planet or orbiting a star in a grand, glittering archipelago. Each cylinder could host a unique biome, a distinct culture, or a specialized function. One might be a vast agricultural belt, its entire inner surface a patchwork of fields and orchards feeding the network. Another could be a preserved wilderness, a national park on a cosmic scale. Another might be a single, continuous city, a metropolis that wraps around itself. This modular approach to living space represents a different kind of ambition. It is not about a single, epic monument, but about scalable, repeatable success. The Alderson Cylinder is the apartment building, the suburban neighborhood, the factory town of interstellar civilization. It answers the need for expansion not with one overwhelming solution, but with a system of reliable, proven components. It suggests a society that has moved past the prototype phase and into an era of mass production, building homes for its people with the same steady, assured pace that it once built cities on its homeworld. This shift from the unique to the replicable is a quiet but profound milestone. It means the dream of living in space is no longer an experimental fantasy, but a standardized reality. Yet, if cylinders can be mass-produced to house populations, what happens when you scale that idea up, not for living, but for a single, unimaginable calculation? What do you build when you need to think a thought that shakes the universe? An Alderson cylinder is a contained world, a finite loop of life, but what if you never closed the loop? What if you kept building, extending that tube of living space in a single, unbroken line that stretched farther than any orbit? This is the 13th concept, the Topopolis, often called cosmic spaghetti. It begins with a simple, scalable design of an O'Neill cylinder, but then it rejects the idea of an endpoint. Instead of capping the tube, you continue its construction, extruding it like a thread from a cosmic spinneret, until it forms a filament of habitable space of essentially infinite length. This world wire would not be laid out in a straight line, of course. It would be carefully coiled into a vast, loose helix, like a slinky wrapped around a star system, or even strung between multiple stars in a delicate, engineered web. The structure's own rotation provides gravity along its entire interior surface, creating a single, continuous landscape that might loop around its sun dozens or hundreds of times. The scale becomes almost a philosophical challenge. The interior surface area of a modest Topopolis could be millions of times that of Earth. You could walk in one direction for a lifetime and never see the same biome twice. Different sections could be dedicated to entirely different environments, a 1,000-mile stretch of tropical ocean, followed by a region of alpine tundra, then a vast desert of sculpted dunes, then a district of continuous urban landscape. Each coil of the helix, receiving slightly different amounts of light from the central star, could have its own permanent climate. The Topopolis fundamentally blurs the line between a place to live and a way to travel. It is both a habitat and a transportation corridor. A high-speed transit system running down the central axis could carry you from a temperate zone to an Arctic one in hours, or from one star to another in a network over years. The flow of resources, air, water, and people would be a logistical symphony, a circulatory system for a world that has no heart, only endless length. It represents the ultimate expression of linear expansion. Where a Dyson swarm is a cloud and a Ringworld is a band, the Topopolis is a thread weaving through space. It challenges our deepest notions of what a world is. Is a world a closed sphere, a defined territory, or can it be a path, a journey made permanent, a single road that becomes home for trillions? The Topopolis suggests that for a truly spacefaring civilization, the concepts of habitat and highway might merge into one, turning the very structure of travel into a place of endless dwelling. A planetary supercomputer represents a more focused ambition than a star-encompassing mind. Where the Matrioshka Brain layers thought around a furnace, the 14th concept, known as a Jupiter Brain, turns a world into a single, dense processor. The name is both literal and evocative. Imagine taking a gas giant, a colossal sphere of hydrogen and helium like our own Jupiter, and methodically transforming it. This is not about building on its surface, but about repurposing its very substance. The planet would be carefully taken apart, its elemental bounty harvested and reforged into a new kind of celestial object, a globe of pure computation. Every ton of matter becomes circuitry, memory storage, and cooling systems, engineered down to the quantum limit. The resulting structure would be a solid, planet-sized computer, its components packed with an efficiency that makes our most advanced silicon chips look like scattered gravel. The raw processing power housed within such an object defies human analogy. It would not merely be faster than all of Earth's computers combined. It would exist in a different category of thought altogether. A Jupiter Brain could simulate entire ecosystems, down to the life cycle of every individual leaf and insect, not as a simplified model, but in atomically precise detail. It could run a perfect, real-time simulation of our own galaxy, tracing the gravitational dance of hundreds of billions of stars over millennia, to predict cosmic events with absolute accuracy. For a civilization that has mastered the art of mind uploading, this planet computer could become a substrate for a vast digital society, a virtual universe contained within a sphere of cooled silicon and superconducting loops, where experiences are limited only by the creativity of the code. While its total energy budget would be less than a stellar Matrioshka Brain, the Jupiter Brain might represent a crucial, intermediate step. It is a project of staggering scale, yet it operates within the realm of a single planetary mass, a known quantity. A species might build its first Jupiter Brain as a proof of concept, a dedicated engine for solving the hyper-complex equations required to design its first Dyson swarm. Or, in a mature interstellar network, these planetary brains could serve as specialized nodes, each one a library, a research institute, or an archival world devoted to a single, immense field of study. The shift in purpose here is profound. It moves a civilization from viewing planets as places to live, or simply as sources of raw material, to seeing them as potential vessels for consciousness itself. It is the ultimate repurposing of matter, from inert gas and rock to organized thought, a silent globe hanging in space that does not harbor life but contemplates it. A planet-sized computer turns matter into pure thought, but what of the worlds we already call home? There is another path, one that does not replace a planet but envelops it, creating a nested series of new worlds from the bones of the old. This is the 15th megastructure, the Shellworld. It begins with a simple, almost conservative premise: do not abandon the cradle, expand it. Imagine taking an Earth-like world and constructing a new sky above it, not a single dome, but an entire second surface, a solid shell held aloft by impossibly tall pillars rooted in the planetary crust below. This new shell has its own ground, its own atmosphere, its own weather. On its outer surface, you could build continents and oceans, lit by sunlight filtered through a carefully managed upper atmosphere. But why stop at one shell? The true ambition of the Shellworld is repetition. You build a third shell above the second, supported by its own set of pillars, and then a fourth and a fifth, creating a layered onion of habitable space around the planetary core. Each layer becomes its own distinct world with its own gravity, a combination of the planet's pull below and the mass of the shell itself. The spaces between these shells are not empty voids, they are vast atmospheric volumes filled with breathable air, creating a three-dimensional living space of staggering complexity. The original planet becomes the foundation, the basement level of a colossal, engineered high-rise that stretches thousands of miles into the sky. The advantages over a ringworld are profound. Stability is the key. A shellworld is gravitationally bound to its planetary core, a stable, central mass. It does not suffer from the terrifying drift of a ringworld, where a slight imbalance spells doom. Instead, it is anchored, rooted in the very geology it seeks to transcend. It also represents a philosophy of intensive, vertical development on a scale that makes every city on Earth look flat. You are not just doubling your living area, you are multiplying it by the number of shells you construct, potentially creating a living volume millions of times greater than the original planetary surface. Each shell could host a unique environment. The lower levels, closer to the planetary core and its internal heat, might be warm, tropical zones. Middle layers could enjoy temperate climates engineered by the flow of air and water between shells. The highest layers, catching the unfiltered sunlight, might be reserved for vast solar farms or pristine wildernesses with skies of a deeper blue than any found on a natural world. The engineering, of course, reaches for the impossible. The materials needed to span continental distances and support the weight of an atmosphere and an ecosystem would need strength far beyond anything we know. Active support systems using dynamic forces rather than passive mass would likely be required, turning the entire structure into a humming, balanced machine. Yet the Shellworld offers a compelling narrative. It is the story of a civilization that loves its home too much to leave it, but has grown too large to stay. Instead of departing for the stars, it builds new ground overhead, turning its sky into real estate and its atmosphere into a layered garden. It is the ultimate act of planetary renovation, a promise that the first world does not have to be the last, only the first floor in an endless tower of possibility. A shellworld builds new ground above the old, a vertical expansion of home. Yet, the greatest expansion for any mind is not outward into space, but inward into understanding. The 16th megastructure embodies this ultimate curiosity. It is the quantum foam telescope, an instrument not for seeing stars, but for seeing the very fabric of reality. This is not a telescope in any familiar sense. You could not look through an eyepiece. Instead, imagine a detector of unimaginable sensitivity, perhaps a gravitational wave observatory with arms stretching millions of kilometers between planets, or an optical interferometer with mirrors placed at the frozen edges of a solar system. Its components would be positioned with a precision finer than the width of an atom, maintained across distances so vast that light itself takes hours to travel between them. The goal is to listen to the universe's quietest whispers, to detect the subtle tremors in spacetime that hint at its fundamental structure. Theoretical physics suggests that at the very smallest scales, spacetime may not be smooth and continuous. It might be foamy, churning with quantum fluctuations, a seething sea of virtual particles popping in and out of existence. This is the Planck scale, a realm a billion times smaller than a proton, where the rules of gravity and quantum mechanics collide. Observing this quantum foam directly is the holy grail of modern physics, a key to unlocking a theory of everything. A civilization capable of building such a device would be using its entire solar system as a single, exquisitely tuned scientific instrument. The engineering challenges are almost metaphysical. It would require a mastery of measurement and control so absolute it borders on redefining what engineering means. Vibrations from distant asteroid impacts, the gentle pressure of starlight, even the subtle heat of the instruments themselves would create noise that must be filtered out. The builders would need to account for the curvature of spacetime itself, the slow drift of planets, and the expansion of the universe over the lifetime of a single observation. Why would a society invest such colossal resources, not in a new home or a greater power source, but in a machine that merely looks? The answer lies in the nature of maturity. A species that begins by asking how to build a fire progresses to asking how to build a city, then a starship, then a Dyson swarm. The final, and perhaps most profound, question is simply, why? What are the rules of the game we find ourselves in? The quantum foam telescope represents the pinnacle of that questioning. It is a declaration that the ultimate purpose of intelligence may not be dominion over matter, but comprehension of the stage upon which all matter dances. The knowledge gained could rewrite our understanding of creation, revealing what happened in the first moments of the Big Bang, or whether our universe is one of many in a vast multiverse. It shifts the narrative from building monuments to seeking meaning, using the grandest possible tools to answer the deepest possible questions. Harvesting a star's light is one thing, but what of the star itself? Its blinding fury is not just energy, it is also substance, an ocean of raw hydrogen and helium fuel that has burned for billions of years. The 17th megastructure is not a collector, but a siphon. It is a starlifting apparatus, a machine that treats a sun as both a power plant and a mine. The concept is audacious: to directly extract mass from a living star, drawing it out in a controlled stellar wind that can be gathered and used. Imagine not just capturing the sunlight, but gently pulling the very plasma from the star's outer layers, funneling it into magnetic conduits for collection. This could be done through intense, focused radiation pressure, or by using precisely tuned magnetic fields to stir the star's surface and lift material away, like a cosmic version of skimming cream from milk. The harvested material is the fundamental currency of a mature civilization: pure hydrogen and helium, the building blocks for everything from fusion fuel to the construction materials of other megastructures. A Dyson swarm provides the energy to build, but starlifting provides the literal matter to build with, closing the loop of cosmic industry. The long-term effects are profound. Over thousands of years, systematically reducing a star's mass would cool it and change its color, subtly shifting the habitable zone outward. A civilization might use this technique not just for resources, but for stellar husbandry, actively managing their star's lifespan and output to maintain ideal conditions for their habitats over eons. This represents a philosophical leap beyond stewardship. It is active stellar gardening. The civilization is no longer merely living under a sun. It is tending to it, curating its properties for the benefit of the ecosystem it has built. The star transitions from an untamed force of nature to a central, managed component of a designed solar system. It is the ultimate expression of a species taking responsibility for its entire environmental context, not just the worlds within it, but the very heart of the system that gives them light and life. This intimate manipulation of a star's life cycle suggests a level of foresight and patience that stretches across geological time, planning not for centuries, but for the slow burn of stellar evolution itself. Starlifting turns a star into a managed garden, a source of both light and substance. But a civilization that has spread its gardens across multiple star systems faces a new and profound isolation. Distance itself becomes a prison of silence. The time it takes for a simple message to travel between stars, years or even centuries at the speed of light, would shatter any hope of a unified society. The 18th megastructure is the answer to this existential silence, a galactic internet. This is not a network of fiber optic cables, but a backbone of light and perhaps stranger physics, spanning the void between suns. Its purpose is simple yet transformative, to turn a scattered diaspora into a single conversation. Imagine constructing dedicated communication nodes, each one a megastructure in its own right. These would not be simple radio dishes. They would be colossal laser arrays or unimaginably sensitive quantum receivers, positioned at strategic gravitational anchors, perhaps in the stable orbits of quiet neutron stars or at the Lagrange points of binary systems. Their sole function would be to catch, amplify, and relay information across the light years with perfect fidelity. The most speculative possibility involves quantum entanglement, a phenomenon where two particles can share a state instantaneously across any distance. If the laws of physics allow for it to be harnessed for communication, these nodes could act as entanglement repeaters, creating a true, lag-free network that binds the galaxy into a single, simultaneous moment. Even without that, a network of perfectly aligned, unimaginably powerful lasers could create data lanes where information travels at light speed, but without delay or degradation. The scale of such an undertaking redefines infrastructure. Each node would need its own independent power source, likely a miniature Dyson swarm or a black hole battery, to fire its beams across the interstellar dark. It would need autonomous repair systems and formidable defenses, for the failure of a single relay could cut off an entire sector of civilization from the whole. The project would require a coordination of resources and purpose spanning millennia, a shared agreement that connection is worth any cost. This network would become the central nervous system of a galactic culture. It would enable not just messages but shared experiences, real-time governance, and an economy where ideas are the primary currency. A philosopher in one system could debate a colleague in another, their conversation flowing as naturally as if they were in the same room. Artistic movements could sweep across star clusters in a matter of years, not millennia. The very concept of alien would fade, replaced by a profound, hard-won familiarity. This suggests that the ultimate megastructures may not be those that provide power or living space, but those that provide meaning. A galactic internet does not conquer space, it dissolves it intellectually. It builds a bridge made not of steel, but of shared thought, creating a cohesive, stellar mind from countless individual worlds. The silent, empty distances that once defined the cosmos become filled with a constant, quiet hum of conversation, a testament to a civilization that chose unity over isolation. This pursuit of connection, however, leads to a final, breathtaking question. What do you build when you want to connect not just minds, but realities? What if the ultimate structure is a gateway to another universe entirely? A galactic internet weaves a tapestry of conversation across the silent void, but what of the silent, steady march of time itself? The 19th concept is a megastructure not of power or habitation, but of pure, enduring memory. It is the Time-Keeping Constellation, a cosmic clock built to measure eons. On the scale of a galaxy, even the most reliable natural processes drift. Pulsars, the spinning corpses of dead stars, slow their rhythms, star clusters disperse. Over millions of years, any natural calendar would become useless, leaving a far-flung civilization without a shared reference for history, navigation, or long-term coordination. The solution is to build a better clock, one that uses the galaxy itself as its frame. Imagine constructing a network of artificial beacons, placed with exquisite care across hundreds of light years of space. These could be engineered pulsars, their spin periods set and maintained with atomic precision, or vast arrays of orbiting mirrors that flash coded signals at mathematically perfect intervals. They would be positioned in gravitationally stable locations, perhaps in the quiet spaces between the spiral arms, their patterns forming a fixed, predictable constellation against the slow whirl of the galaxy. From any point within its range, an observer could measure the precise timing of the signals from multiple beacons. By comparing their rhythmic pulses, one could triangulate not only position in space, but position in time, maintaining a calendar that remains synchronized across the entire region for millions, even billions of years. This is a clock built from the architecture of spacetime, its ticks measured in the flight of photons between constructed stars. The purpose is profoundly cultural. It provides a permanent backbone for deep time navigation, allowing voyages or messages launched millennia apart to arrive with perfect coordination. It becomes the ultimate historical record, a way to timestamp events, discoveries, or even the completion of other megastructures, creating a unified chronology that future generations or other species could decipher. Most importantly, it is a legacy. The Time-Keeping Constellation speaks not of what a civilization built, but how it thought. It reveals a mindset that planned not for the next election or the next century, but for the next galactic rotation. It is a monument to patience and precision, a silent, ticking message to the future that says, "We were here, we measured the universe, and we left a measure for you." This shift from building for utility to building for memory leads us inevitably to the final, most profound ambition on our list, a structure that seeks not to preserve a moment in time, but to escape time's dominion entirely. The final tick of the cosmic clock is a measurement of eternity, but what if the goal is to step outside of time altogether? This brings us to the 20th and final theoretical megastructure, the most profound and speculative of them all, the Transcendence Engine. It is not a home, a power plant, or a computer. It is a bridge. Its purpose is singular and staggering: to facilitate a civilization's transition beyond the physical universe as we understand it. After mastering matter, energy, and space, this represents the ultimate frontier, the architecture of reality itself. Imagine a construct that merges the star-spanning computational depth of a Matrioshka brain with the space-time warping intensity of a black hole farm, all fueled by energy sources we cannot yet name. This engine would not be built to sustain life within this cosmos, but to explore what lies beyond its fundamental rules. Its theoretical functions read like the dreams of a deity: to manipulate the vacuum energy seething within empty space, to create and stabilize wormholes to other universes, or to trigger a controlled, local phase transition in the very laws of physics, perhaps creating a bubble of new reality with different constants, a custom-made cosmos. This is the end game of megastructure engineering. It answers the final question of growth: what does a civilization do when it has comprehended its home universe? The answer may be to build a doorway and step through. The Transcendence Engine lives in that rare space where rigorous theoretical physics blends into a new kind of metaphysics. It asks what the ultimate grand project of a mature intelligence could be: not to build monuments within the universe, but to engage with the substrate from which the universe is made. It suggests that the final act of a cosmic civilization may not be an act of construction at all, but an act of metamorphosis, using the last and greatest of its tools not to change its environment, but to change the nature of its existence. This concept completes our journey through 20 layers of cosmic ambition, from harnessing a star to contemplating an escape from reality itself. Each structure we have explored, from the practical orbital ring to the philosophical time-keeping constellation, represents a different answer to the question of what a species does when it looks up and decides not just to visit the sky, but to move into it and eventually to reshape it. These are not blueprints for next year, they are visions for the next million years, stories we tell about the furthest potential of mind and matter. They remind us that the universe is not just a place to live, but a place to become, and that our greatest adventures and our greatest constructions may still be ahead of us waiting in the starlight. These 20 cosmic ambitions form a ladder of possibility, each rung representing a new relationship between mind and universe, from the foundational energy grid of a Dyson swarm to the metaphysical doorway of a Transcendence Engine. They chart a course not just through space, but through the potential stages of a civilization's growth. This is a future sculpted from patience, a timeline measured in the slow burn of stars rather than the fleeting span of human lives. It asks us to adopt a new kind of patience, to think in units of time that feel more like geology than history, where a single project becomes the defining purpose for generations upon generations. The true value of these ideas may not lie in their eventual construction. It lives in the pressure they place on our present. To even sketch a Ringworld requires breakthroughs in materials science we cannot yet fathom, pushing us toward stronger alloys and smarter, self-repairing structures. The concept of a Matrioshka Brain forces us to wrestle with the physics of computation at its absolute limit. Each theoretical blueprint, however distant, illuminates a path of inquiry for today's engineers and physicists, turning science fiction into a catalyst for real-world innovation. On a deeper level, these megastructures serve as a profound thought experiment about destiny. They hold up a mirror to our own species, asking what we would do with such power and time. Would we build arcs to preserve life or engines to escape reality? Would we focus on connection, building a galactic internet, or on introspection, constructing a quantum foam telescope to understand the stage upon which we stand? The answers we gravitate toward reveal our own hopes and fears for the future. They challenge us to consider the legacy we wish to leave, not just on this planet, but as a potential voice in a silent cosmos. So, as the stars wheel overhead, consider this invitation to dream on a cosmic scale. Which of these vast visions resonates most with you? Does the elegant simplicity of an orbital ring, a key to the solar system, spark your imagination? Or does the profound mystery of a stellar engine, gently nudging a sun on a million-year journey, stir a deeper wonder? Perhaps you have an idea for a 21st megastructure, a concept waiting to be sketched on the canvas of the possible. Share that vision below. Join the conversation about what comes next. If journeys into the edges of science and discovery inspire you, subscribing ensures you never miss an exploration. The universe is not a finished work. It is raw material waiting for the touch of intelligence, patience, and will. Our future is not a pre-written story, it is a project, and we have only just begun to read the plan.